Okay, so now in this video series we've been going through a practice AP calculus test that I've written, and what we're going to do now is we're going to tackle the next section, which is the calculator free response section. Alright, now normally this is a 2-question section, but since I've cut this in half, I've made it a 1-question section, and there's going to be 15 minutes to do this one question. Alright, so section 2 part A is the calculator free response. And as you can see here, a graphing calculator is required for this problem. You cannot do it without a calculator. Okay, so without further ado, let's get started. Look at question 1. Let f of x equals e to the negative 2x minus 0.1 and g of x equals ln x plus 1. Let R be the region bounded by the graphs of f and g in the y-axis. Let S be the region bounded by the graphs of f and g in the x-axis. R and S are shown in the figure above. In part A, we're asked to find the area of S. But before that, we have a couple of preliminary things we need to do. First off, I want to actually label f and g because it's not really given here. Okay? So for g's, I know it's ln of x plus 1. I know ln is an increasing function, so I'm going to mark that as g of x. And I know that e to the negative 2x, because that negative there is a decreasing function, so I'll mark this as f of x. Okay? Now, the next thing I want to do is I want to pay attention to this important point here, because that's the intersection point of g and f. And that's going to be really important when we're defining this region R and this region S. So I want to calculate this intersection point. Okay, so the intersection point, how you do that is you're going to set g of x equal to f of x. So you can graph this in your calculator. You can make y1 f of x, y2 g of x, and then find this intersection point. And if you do that, you'll get 0.408, comma 0.342. Okay, that's the intersection point. And now, the second thing we need to do is figure out how to find the area of S. Right? The problem you'll notice when we try to find this area is that there isn't really a top curve and a bottom curve, but rather there's a left curve and a right curve. Now there's 2 different approaches you can take. One is you can draw a vertical line here and find the area of this region, and then find the area of this region. And the second method, and which is the one that I'm going to show you here, is by taking everything in terms of the right curve and the left curve. Instead of top minus bottom, we're going to do right minus left, okay? And to do that, we have to switch everything horizontally. So instead of y equals something with x, we'll have x equals something with y. So since we're turning everything in terms of y equals, so in terms of x equals something, we have to solve each of these equations for x. So for f of x, right, we have e to the negative 2x minus 0.1, we need to solve this for x. Okay, so I'm going to add 0.1. Remember, f of x is just y. So I'll get y plus 0.1 equals e to the negative 2x. And I'll take the natural log of both sides. And I'll get that the natural log of y plus 0.1 equals negative 2x. And then I can solve this for x. And I'll get x equals ln y plus 0.1 over negative 2. Okay, now I can do the same thing for g of x, where g of x is equal to the natural log of x plus 1. So I can put e as the base for both of these, and I'll get e to the y equals x plus 1. So x equals e to the y minus 1. Okay, now that I have that set up, all I need to do is say, alright, so this is my right curve, right? F of x is my right curve, and g of x is my left curve. So when I set up my integral, which is going to be the integral of the right curve minus the left curve, well, this is the right curve, ln of y plus 0.1 over negative 2 minus the left curve, which is e to the y minus 1, right, dy. And what we're doing here, just to be clear, is we're finding this horizontal distance, right? That's why we turn to everything in terms of x. We can remember x equals this, because we want to find this horizontal distance here, and that's in terms of x, right? This horizontal thing, here's x equals something, here's x equals something else. So that's why we were turning everything in terms of x, and this horizontal distance is represented by this expression. Now what we want to do is we want to add up all of these distances from this point all the way up, so we're adding up all of these lines from y equals 0 up till y equals whatever this point is. And like we found before, this point here is 342. So we're going from y equals 0 to y equals 0.342. We're adding up all of these infinite lines. So we're going from 0 to 0.342. When we add that up, we'll get the area of this region S. if you were to put this in your calculator and evaluate it, you would get 0.171 as your answer. Okay, that's part A. Part B asks us to write, but do not evaluate, an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 1. So let's look at that horizontal line y equals 1. It's right here. Okay, and so I'm rotating r about this region, right? So I have two different curves that define r. So I'm going to define two different radii. We have this guy, I'm going to call it little r. This guy, I'm going to call it big R. Okay, those are the conventions used. Don't get this big R confused with this big R. You don't even use different variables like little a and big A, I guess. It doesn't really matter. So anyways, what we're going to do is we're going to say, okay, if I can find little r and big R, I can just plug that into my expression to find the volume of rotation, and that's it. Okay, so little r is going to be the distance from, remember this is y equals 1, the distance from y equals 1 to this curve. And the way I like to do that is by saying, okay, this entire distance here, from y equals 0 to y equals 1, this distance is 1, right? But I don't want this entire distance, I want the whole distance, but I'm subtracting out this height, right? Subtracting out the distance from y equals 0 to y equals f of x, right? So this distance is f of x, and I'm subtracting that from 1. So this is 1, and this is f of x. This is 1 minus f of x. So little r is 1 minus f of x. Right, similarly, I can say this whole distance is 1, and this distance here is g of x. So the big R is 1 minus g of x. Right, that'll give us this leftover distance after we subtract out the g of x part. Okay, now that we have our little r, which is 1 minus f of x, and big R, which is 1 minus g of x, I can just use my equation, which you remember is the integral from a to b of big R squared minus little r squared dx times pi. Okay, so I can just plug in my little r and big R, and my a and b in this situation, that's going to be my starting point and my ending point. So I'm starting right here at x equals 0, and I'm ending right here at x equals 0.408. So I'm going to be above pi times the integral from 0 to 0.408, and big R squared, which is 1 minus g of x squared, minus 1 minus f of x squared dx, right? Now the final thing is substituting g of x and f of x in. Okay, now I have it written down on my paper here, so I'm just going to save you the time of going up and down and up and down, and I'll just write it here. Right, so it's going to be 1 minus, g of x is ln of x plus 1, so 1 minus ln of x plus 1 squared, minus 1 minus f of x. So f of x is e to the negative 2x minus 0.1, so it's going to be e to the negative 2x minus 0.1, there, squared, dx, and there's your answer. Okay, squeeze that in there, there we go. Okay, there's your answer. Okay, and now let's move on to part C, which says the curve g of x is replaced by the curve h of x equals ln of x plus k, where k is a constant. If f and h intersect at the point a comma b, write but do not evaluate an integral expression to find the value of k such that the areas of r and s are equal. Okay, so this is a prime example of a question that is a lot easier than it looks. I admit this does look a little bit intimidating, but it's really not that bad. Okay, so basically what we're doing is we're trying to find a value of k, and we're trying to make the areas of r and s equal. Okay, so since I want r and s to be equal, my strategy here is going to be I'm going to find an expression for r, and then I'm going to find an expression for s, and I'm just going to set them equal to each other. Okay, that's it. So let's start with r. Okay, so I'm going to go up and I'm going to say, how do I find the area of r? Okay, and by the way, so basically, let me explain real quick what h of x is. So h of x, we're replacing the 1 and we're just replacing with the k, right? So what that's going to do is that's just going to move this curve. It's going to move it different places along here, okay? So right now it's moved here, right? The 1 moved it to this position, and different values in place of 1 are just going to move it different locations around here, okay? So basically, I want to move it to the place where r and s have equal areas. All right, so for r, notice that it's this curve. Let me erase this stuff, actually. It's kind of getting in the way. But notice for R, we have f of x is on top and g of x on the bottom, right? And in part C, g of x became h of x. So I'm going to refer to it as h of x from now on. So we have f of x on top and h of x on the bottom. So this vertical distance is going to be f of x minus h of x, right? And like we did in part A, except now it's right back into, instead of doing horizontal lines, we're doing vertical lines. I have this vertical distance, and I'm integrating it from 0 to whatever this point is. And we're given this is the point A comma B, right? So this horizontal distance is going to go from, I keep saying horizontal, this vertical distance, we're integrating this vertical distance across 0 to A. So going from 0 to A, and we're integrating this distance, which is f of x minus h of x. Okay? So for R, it's going to be the integral from 0 to A of f of x. It's just like we did in part A. It's literally like the exact same thing, except it's easier because now we're dealing with vertical lines instead of horizontal lines. So we don't need to rewrite anything in terms of y. Okay? And now I'm just going to plug in whatever I have. So it's going to be the integral from 0 to A. F of x stays the same. It's e to the negative 2x minus 0.1. And h of x is going to be the ln of x plus k dx. Okay? Now I can do the same thing for s. S is actually going to be even easier than R because in part A, we said that the area of S is the integral from 0 to 0.342 of ln of y plus 0.1. I'm just repeating our answer from part A here, minus e to the y minus, not 1, right? Minus 1. Okay? dy. So this is what we said in part 1, but now all we have to do is modify this answer to help us in part C. So now instead of going from 0 to 0.342, we're going from 0 to b, because b is the y value of the intersection point. And also in here, instead of minus 1, we're going to have minus k, because the number 1 got replaced with the number k here. So this is actually the area of region S, right? So now we have an integral expression for region S and an integral expression for region R. Now all that's left is to set them equal to each other, okay? So I'll say R equals S. So this integral, which is the integral from 0 to A of e to the negative 2x minus 0.1 minus ln of x plus k, equals the area of S. So this is the area of R, and now here's the area of S. 0 to b of ln y plus 0.1 over negative 2 minus e to the y minus k dy. Okay? And that is our answer. This is setting R and S equal to each other, and if you were to evaluate this integral expression, which I'm not asking you to do, you would get the value of k. Okay? And that is it. That is the end of this question, alright? So hopefully it wasn't that bad. It might have seemed a bit complicated, but hopefully you realized it's not really that complicated in real life. So yeah, that was the end of section 2 part A. Like I said, there's only one question. And next time we'll look at section 2 part B, which has two free response questions, and we'll have 30 minutes to solve those. Okay? I hope you enjoyed this video, and I will see you in the next one. Make sure to like and subscribe. Goodbye.